Okay, so in this problem, we want to construct the influence line for the bending moment at point C. So our strategy, as we've talked previously, is to find the moment at C, we're going to need to cut the structure. So let's just imagine the structure cut at C. And now which side do we look at? Do we want to draw a free body diagram of the left side or the right side? Yeah, I don't really see much difference, but I think the left side will be a little easier and a little cleaner in keeping track of our position. So I'm going to decide to do the left side. And once I've made that choice, you can see I'm going to need to know something about AY. So I'm going to come over here and I'm going to draw a free body diagram and assume a direction for AY and BY. The distance between those is 10 feet. The overhang is 5. And then I'm going to assume here's my unit load at some distance X. Now since I'm looking for AY, I'm probably going to sum moments about BY, so I'll be interested in the distance from B to the unit load. And what will that be? Looks like the total distance is 10, so it would be 10 minus X. Everybody see the geometry? So with that said, let's sum moments about B. Make sure it's in equilibrium. So around B, the unit load creates positive or negative moment? Positive. So force times distance. And then AY about B creates negative moment. Force times distance. So let's solve for AY. And it looks like AY is going to be equal to 1 minus X over 10. So that's really the influence line for AY. And you could plot that if you like. And it would look something like this. So that would be 15. Okay, so when X is equal to 0, AY is 1. When X is equal to 10, it's 0. And when X is equal to 15, AY is minus a half. You guys see that? So the maximum reaction at A for my moving load is when I'm at X equals 0. So when I'm standing right on top of A, I'm creating the maximum moment at A. Maximum reaction at A. And as I move over to B, when I'm standing on B, that's this point, I create no reaction. And as I move out on the end of the cantilever, the reaction changes direction and is pulling down. The maximum value there would be half the load. Now the problem wants the moment at C. So I'm going to come back now and look at this free body and have two cases. One where my unit load is on the free body from 0 to 5, and then I'll look at it again when the unit load is between 5 and 15. So I'll preface this by saying the unit load between 0 and 5, now this is the unit load position. My free body diagram will look like this. I have 5 feet. I have my reaction at A, which I've solved as 1 minus X over 10. I have my bending moment at C. That's the positive bending moment. Here's my unit load at some distance X from the left side. So what's the distance of the unit load from the cut? 5 minus x. So now I have all the pieces I need to find the internal moment at C. And I can do that simply by summing moments at the cut. Make sure it's equal to 0. So let's just take an accounting of them. The moment at C is positive moment. This unit load of 1 about the cut also is positive. So there's force times distance. Then all the way out here on the end is this value, which is going to create negative moment. Force times distance. So I need to solve for the moment at C for all that. Let's see what I've got. This is just 5 minus x. And this is minus 5 minus x over 2, right? Or plus x over 2. So 5 minus 5 cancel out. I've got negative x plus x over 2 is negative x over 2, right? When I throw it to the other side, it just becomes positive x over 2. You guys see that?
So, you went from 0 to x to 5.
We cut it at C because that's what the problem wanted, right? We want the moment at C. So I cut it at C, and we decided to use the left free body. So when the unit load is anywhere between 0 and 5, this is the situation.
The load would be somewhere.
It's any position you want x, but it has to be between 0 and 5.
Okay.
Now what happens when I have the same free body diagram? I'm still looking for the unit load. I'm sorry, still looking for the moment at C. I still have my influence of my reaction. The structure is still 5 feet, except the unit load is now between 5 and 15. Which means it's not on this free body. It would be over here somewhere now. So, does this object still have to be in equilibrium? Yes. So let's find what it is. So if I sum the moments now at the cut, what does the structure say? Well, that's positive moment at C. This reaction force creates negative moment, so that'd be minus 1 minus x over 10. That's the force. And what's the distance? 5 feet. So when you solve for the moment at C, it looks like you get 5 minus x over 2. So now we just need to plot those. So if I plot the moment at C as it varies across the structure. So there's 15, there's 10, there's 5. Okay, so for the first 5 feet, I use this equation. So starting at x equals 0, I get 0. At x equals 5, I get a positive value, 5 divided by 2. You see that? Now from 5 to 15, I have to use this equation. So when I put in x equals 5, what do I get? 5 over 2. So it matches. What's this value when x is equal to 10? 0. And what's the value when x is equal to 15? Minus 5 over 2. Guys see that? So the moment diagram does not have a discontinuous jump like the shear diagram from a couple problems ago did. So I'm looking at this problem now. What's the maximum moment at C? Well, what's the largest ordinate value? It looks like it's 5 halves, but one's positive and one's negative. Now, in moment, does it matter about positive or negative moment? It does. Think back to your reinforced concrete experience. So a positive moment, this structure would be bending concave up and your reinforcement would be in the bottom. Over here you have a negative moment, it would be concave down, your reinforcement would be where? In the top. So a diagram like this might tell you how to handle your moment. Now this is a moving load. Alright? So it says the moment at C can be both positive and negative. So you have to have both tension steel and compression steel, if this were concrete, at the same point because of the moving load.
So you can solve for either the left half or the right half of the beam to find the moment at C. So if you did that, then the length of the beam would have been 10 feet from 0 to 100.
If you were to solve this section, you'd have still written an equation when the unit load is between 0 and 5.
Right, and
another one when it would be 5 and 15. But this free body, for the first one, would not have the unit load on it.
Right. But it would be the same one. So it'd be like reverse.
Yeah, if you just want to see that, what I'll do is I'll just kind of tuck those free bodies down here in the corner. I won't go through the equilibrium, but this is what it would look like if you had chosen the right-hand side. So from 0 to 5, your free body diagram would have looked like this. We would have had the positive moment at C. Now, I don't know what the reaction By is. We would have to go get that, right? And that would be it. Because the unit load is between 0 and 5, and this is 5 to 15. The second case, when the unit load is now between 5 and 15, then your free body diagram looks like this. This is still the moment at C. This is still the reaction By, but now the unit load would show up. And you'd have to work on these distances. This is the distance from here to here would be x, but this distance would be it would be x minus 5 or something like that. This would still be 5. When you solve for this equilibrium, you will get that result.
No matter which side you put the load?
No. And when you solve for this one, you would get that result. Now, of course, we don't know what By is. We'd have to find. Remember, we started the whole problem by finding Ay. Okay, this By would be different. It'd be a different value. So any other questions about this one?
Just curious. Do you mind if it's in fraction form or decimal?
I don't mind. I like fraction just because I don't have to worry. I use my calculator. Kind of lazy.